So what is the science behind all this? How does it really work? Is it a matter of a lot of windings or a lot of copper? Or is one winding as good as a million windings? Let's make a very little experiment instead of just talking a lot of theory. So I think it's more visual to show this, by a practical experiment. Then you will understand the physics a lot easier. So here's the first experiment. Let's take 10 windings of this copper wire, single core insulation wire, right? So 10 windings, and then we connect these together, and then we see what is the output under load, under hard load, by the way. So this is 100 VA secondary. I'm going to try and load it with 60 watts. Of course, I know it's not going to deliver, but we're going to write down the output voltage and current and input voltage and currents and everything. And then we're going to see what we get. And then we're going to try and do 10 single windings. So that means we have exactly the same copper, 10 single instead of 10 in series. And then we're going to see if there's any difference. All we need to do is actually measure the output under load, and this way determine how we get the best coupling, right? So what I've done is this is 10 turns in series, right? And let's try and turn it on. Yeah, 201. Ooh, you can hear it's it's humming a little bit. Oh yeah. All right. So that was the first experiment. So this is going to be interesting. Only one turn, exactly the same wire. What do you think is going to happen? Let's turn it on. Ooh, this is difficult with one hand. That's it. Really? Is that really connected? Yeah. 5 volts when it was cold. It's running insanely hot, obviously. Because now the current that we're trying to pull is way too high compared to what this wire can handle, right? But we're gonna put in 5 volts. So let's try this with 2 windings. All right. 37. Ooh, let's turn it off again, okay? Yeah, it's really, really hot. All right, let's try and double the 2 turns to 4 turns, and let's have a look. 103. And, oh, this lamp is annoying. All right, 6 turns. 150. And this is 8. 182. So let's do the last one. 10 turns of single wires like this. Let's crank it on. 210. When it was cold, of course, it's going to get hot. Yeah, now it's not that bad actually. Let's see. After a little while, we're down to 201. Ooh, I can feel it is suffering. Let's try something really, really interesting. Let's go back to the more or less the original mode, but again, the same wire, the same 10 windings on one and 10 windings on the other, and then just connect them together, just like you would done the good old style, right? So What do you expect this one is gonna do? Let's have a look. Only 172. Really? So let's look at all the three results at the same time. It was 201, 210, and 174 volts when the windings were cold. So that is quite a big difference. Now let's try and understand exactly why it is like this. Let's examine the primary side of a transformator just like this. See, if I hold the wire in the center, I get 200 millivolts, and the wire is just very big and open and far away. So this is only the center. See, if it is at the edge and all the way around, I get exactly the same. I can even put it more around the core like this, and I'm still getting exactly the same. So all the magic is in the hole, right? Doesn't matter where in the hole, but it is in the hole, all of it, right? Let's try and do the same experiment with the outside of the core. So again, we're taking the wire to the voltmeter, and then let's try and measure from the outside. Is there anything to pick up from the outside? No, there's not. See, I can even try and take it all the way around from the outside. That means the ends is like open, both ends open like this. Let's try and put it all the way around the outside, and you get absolutely nothing. Of course, the inside, where it is actually generating something, it goes forward and back again. So this is why you don't get anything, even if you pull it all the way through like this, because of course the wire goes back and forward the hole. Alright, fair enough. I got a few comments about voltage versus current. So this is one shorted wire directly into the meter, but now it's in amps. So let's see how many amps can we get. See, here's the 200 millivolts from the one winding. So now we go to amps, and we have 3.37 amps for the same one winding. And again, doesn't matter if it's in the center, up in the air, or down to the core, or all the way around the core, you get exactly the same output. So that is very interesting to observe. The difference that I get here is actually just because I'm poking around with the wires, and so the two hooks, they move a little bit, but see now here I'm not moving anything. I get exactly the same voltage. Alright, so for the experiment it doesn't really matter. One here is bigger than the other. This is just what I happened to have around here, right? So anyway, we just learned that everything happens in the hole. And that means this distance and that distance and that distance down here is just wasted length. This length is of course also wasted. And again, waste, waste, waste. It's only happening in the hole, right? And so we're generating 200 millivolts for one winding. So in this case, we have 2 volts. And then I transport the 2 volts over here and get my power back again, right? But since I'm trying to light up a 60 watt bulb, then the current here is of course insanely high, right? It's in the 30s of something amps. So of course I'm totally overloading this wire, and that means every little milliohm that is inside this wire counts a lot. So that means all the wasted length here is just so much loss. That is, the loss here is so dominant for this experiment. Okay, let's measure the current, shall we? So here's a current probe. It is in 100 amp mode. Let's look at the, 35 amps. So that's 35 amps for 1.5 square millimeter copper. This is of course why it's getting really, really hot. So if I have 10 windings, if I put this real close, remember the winning experiment was B, the shortest possible wire around, and then it was assembled. So that means, so why was the 10 single wires in parallel, why was that about 10% better compared to just one going around? It was looking like on the pictures like it was the same length, right? There was only one assembly joint, and then it was actually a lot worse. So B was the winning experiment because of the 10 assembly joints, because of each of these assembly joints is like 1.5, almost 2 centimeters overlap. And when you do this 10 times in this experiment, it actually adds up like one extra winding. So that is about the 10% extra extra copper, right? And that is why B was winning. The copper resistance here is insanely important. So let's try and imagine how we can make this better, right? So how can you put them closer so that all the length that you have between them is as short as possible and as thick as possible? And of course, what you need is the copper here in the magic hole where everything happens. This must be as thick and as massive and as solid as absolutely possible. But of course, you also want distance to the other winding because you want less capacity. That was the whole idea of all this. That was the low capacity, right? So, solid center and then go big and wide and massive. Here, out here, you can do it as big and as thick and as massive as you want, as long as you still have distance to the cores. And then you do this on both sides, you'll be able to make a big winner. So, in this one, I do have 2 assemblies or 2 connections, and that is of course not how I would recommend to do this again. Of course you want to have only one, but you want to do it over a long distance so you will be able to get a very, very good connection. But you also want to double the copper that you have here on the long length. So let's say that you have only one connection here, for example. Then of course the overlap here will make the copper double. I don't know if it's easy to see this, but this is actually, of course, double the area compared to what I have in here. It is actually almost filled up here, right? So how do you double the other side if there is no connections over here? You just take, again, the same copper and just put it all the way around again here and just squeeze it all together. Then it will, of course, help with the transport of current here. So why is this important for this one? Because this one is nearly 2000 amps. That is absolutely crazy. And the milliohms or the micro-ohms in this one is very, very important. This is why I've done it like this.